Okay, so SWAT. This was a software-based attestation mechanism developed here at CMU by one of Adrian's graduated students. I think this was the introduction of the pseudorandom memory traversal. Is that right? Or it was already there? No, okay. Well, it makes use of the pseudorandom memory traversal. And it was intended largely for relatively simple processors, so nothing superscalar, no out-of-order execution. Did they even have caches? No caches. So a system where it's easier to reason about how long would you expect this to take. You know, if there's no cache, then each memory access takes the same amount of time, and you just have to count up memory accesses instead of worrying about whether it's going to be a cache hit or not. And it's actually pretty interesting. The verification function for SWAT is not a hugely complicated function, and the best attack that we know of on it actually only amounts to adding 1 or 2 instructions in this function, and it just iterates so many times that eventually the attacker's execution time will diverge from the expected execution time enough to be detectable. So I think I've described some of this, but time is this externally detectable property that we add in addition to just checking that the hash or the checksum result is the expected result. And so the hard part is really to design a checksum function that slows down if the code is modified. In a perfect world, we would have a mathematically proven to be optimal checksum routine that does this pseudorandom memory traversal in order to eventually accumulate, with high probability, at least one reading of every address in the memory of the system. And so the attacker, because he can't predict the order of this memory traversal, is going to have to check each memory access and say, uh-oh, is that a location that I changed? Right? Even if it's just one test instruction in this checksum routine, that's going to actually end up being a detectable overhead. So one of the early SWAT function was kind of a position-independent function. And one of the things that the attacker could try to do is a memory copy attack where they move the checksum function to some unused region of memory. And so a bit of insight is that it's useful to include code's position information in the checksum routine. So, for example, include the program counter and include the data pointer to exactly which address is being read and incorporated into this checksum routine. Kind of to me, the spirit of it is similar to explicitly naming the parties in your network protocol. But again, we want this property that if you try to forge the program counter or you forge the data pointer, the execution time of this routine is going to increase. You're going to be able to detect that. So this brings up an interesting challenge, which is that there are some hardware platforms or architectures out there where you can't just read the PC in one high-speed instruction. I think even x86, you have to call the next instruction and then pop that. So you end up doing a push and pop to the stack. Even if it's in cache, that's a lot faster than a register-to-register operation, or rather slower than a register-to-register operation. So, taking these additional mechanisms into consideration, we end up with a design called ICE, for indisputable code execution. And this is a little bit more concrete of a checksum routine that can actually try to give us these properties on a real system. And so, one of the properties of the pseudorandom memory traversal is that it needs to be non-parallelizable. So if you can somehow do something clever by computing the checksum over 2 regions at the same time or any other kind of parallelization that you can think up, you might be able to get the right answer in a shorter period of time. And so one of the functions that's used in the indisputable code execution solution is something called a T function, which is a series of multiply and XORs, I want to say. Where's the multiply? The move? Okay. So this is an example of one of the checksum routines that's been developed, and you're certainly welcome to study it in more detail and ask questions. Actually, does anyone want to ask a question now? Yeah.
Be a way of circumventing this calculation? I mean, it may be a big table, and it may be improbable that you get a hit that's in your memory space, but, I mean, you could pre-compute all this, and then you end up being able to do the lookup faster than it would take you to read.
You're not able to pre-compute it for the entire memory contents. I mean, this is like an extend operation for every 32-bit word in memory or something. And so
wouldn't it all be reasonable to guess a limit of where the space is likely to be and then pre-compute?
Yeah, there's a nonsense changes.
I'm not sure what you mean by where this space is likely to be. But no, these are good questions. So
the probability is perfectly distributed across the entire space.
That's an intention.
And it's like big enough. The value is big.
Well, the checksum result is kind of accumulated, right? It's this isn't actually a hash function, but it's very similar to a hash function where each new value takes into consideration the previous values, and so you have a complete history of the order in which you traversed all of memory. So.
Could I keep racing this until I have to?
When you say hit, you mean a collision? I mean,
no, I mean a hit with a table, so that then I could do a faster table lookup. I mean, can I keep on triggering this?
I don't know where you're going to keep your table. So one of the assumptions, maybe I didn't make that clear, was with the way that we have a good understanding of the hardware architecture, we know precisely how much memory is there. If the attacker's got some place to store their lookup table, then that violates the assumption for this mechanism. That would be kind of, we don't understand the hardware platform that we're trying to interrogate. If your lookup table becomes big enough to conceivably be useful, then I think you've interfered with the intended contents of memory to the point where you would really need a seriously compressible, legitimate executable. Do you want to add something?
Yeah, checksum state is huge. It's like 1,000 bits or more. Good luck trying to get a hit.
It'll be
Yeah, so the point was that the checksum state is big and that the likelihood of getting a successful lookup is probably extremely low. Okay, so software attestation is an exciting primitive. It's pretty remarkable that you might be able to get the properties similar to this dynamic rooted trust operation without having to have the hardware support for it. It works on legacy systems or embedded systems. Actually, the simpler the processor, the better. So on these older legacy systems, sometimes it's actually easier. You don't need secrets, and since it's software only, it can be applied in a lot of environments. The research challenges are that we do require this very detailed knowledge of the exact hardware architecture. There are hardware architectures that are sufficiently complex that it's a real challenge to come up with one of these verification functions. We have not formally proven that the verification functions that we have are optimal. There's not a clever way to do better. And then the exact amount of overhead induced by the best known attack. So I talked about this memory copy attack requiring maybe an extra test instruction on each iteration of the loop. That's not a huge time difference, and so you need to iterate, over memory addresses for a while to get enough of a deviation that it's easy to measure the overhead. And that can be a problem in a practical scenario. So maybe your detection fidelity is like 10 milliseconds. So once there's 10 milliseconds of overhead, you can detect that. But to get a 10 millisecond difference between the legitimate execution and the malicious execution, maybe that takes 5 seconds. And so whatever device it is that you're trying to interact with, all of a sudden it's, interrupts disabled, appears from the user's perspective to be frozen for 5 seconds in order to run long enough to get this, 10 millisecond overhead. So these are just a few examples of the open research challenges, but